All right, good morning. Hopefully we'll have some more people coming into the stream. I know I got it up kind of late. I got it up at 8 instead of 5 to 8 like I normally do. I hadn't realized I didn't press the start streaming button. So hopefully people will figure that out and come on in. Starting a very important topic today. So let's see. Let's just double check back here. Where are we with the project? Yeah, we're good. Okay, so just be aware. I know you still have some time to work. Sorry for the noise. The lawn's being mowed right now and worked on. It should end pretty shortly, if you can hear that. So chapter 9 is really about confidence intervals, right? Estimating a parameter, a population, or a proportion, or a mean. We talked about those last time. Really important. You should definitely have those in your project, right? And again, probably not just one. When you're looking at the project, don't think of it as a checklist. Like, I have a confidence interval in there. Maybe have 2 or 3 confidence intervals depending on your data, right? Really show me that you know what you're talking about. Those are, that stuff's due. We have a little bit more time, but things are going to move quickly for the remainder of the semester is going to move quick. So watch that and then make sure, right, you still good chance to get a pretty easy 10 points that go towards your project grade right here up on November 30th. Just show me some confidence intervals basically, right? And make sense of them. Remember, if all you do is like read a confidence interval to me, you can get very, very minimal points. If you give me a confidence interval and then give me some kind of conclusion or something that goes with it, I'm much more likely to go, okay, this person understands what they're talking about. They're not just, it's very easy to punch some buttons in StatCrunch and then read what StatCrunch says. That doesn't show me that you understand statistics at all. So make sure that you're including those interpretations, those conclusions, that kind of stuff, especially in your final product, the video that you'll be presenting to me. Today we're going to start the last big topic of the course, which is hypothesis testing. And it's important. You should probably have numerous hypothesis tests, right? Every project is different, but you should probably have numerous hypothesis tests in there. And again, make sure that you're stating things correctly. If you just go, oh yeah, I read that like a few weeks ago, and you make up your own conclusion, it's a good chance you'll be stating things incorrectly. So make sure that you're, paying attention when you're watching the videos, because a poorly worded conclusion on a hypothesis test is bad as far as points, right? It's like, oh, this person doesn't actually understand what the hypothesis test does, because it's a little bit confusing, right? It's a little bit confusing at first when you first learn it. There's a number of subtle points where the logic involved in understanding the hypothesis test is subtle. Right? And people go, no, I get it. I get when the P value comes out like this, I'm supposed to reject the null. I know exactly what's going on, right? But then when you push them on, okay, so conclude that for me. Sum up what your hypothesis test says about your data. They go, I don't know, but I rejected the null. Okay, well, what does that mean? How does that help anybody that you rejected the null? You're not going to go to your boss at work and say, I rejected the null, which, of course, you don't know what that means yet because we haven't talked about it. But just imagine that. If someone walked into a room and said, hey, I rejected the null hypothesis, you're going to go, I don't know what you're talking about. What you have to be able to do is take your statistics and put it into a useful conclusion for your work or your research or whatever you're doing. I mean, literally, if you don't do that, this whole class was a big waste of time. It will be pointless, because StatCrunch is the one that's actually calculating the hypothesis test and crunching all the numbers, right? So it's really like StatCrunch took the course, if that's what you're doing. You have to go beyond that and know, I can take what StatCrunch tells me and I can make a useful conclusion about that, right? About, if we think that there's lots of hypothesis tests that we could do, but make some kind of conclusion about your particular data that you're looking at. Okay, that's what I would like to see. Otherwise, I'm going to go, okay, you memorized how to punch some buttons in StatCrunch. You get a very low score for that. So we're going to go through what hypothesis testing is about. We may or may not finish that by Thanksgiving. We'll have to see, which is a week from now. We'll have to see how that goes. We may or may not finish it. And then afterwards, things are going to happen fast when we come back. But I'd like to open it up, and I'll talk about the project. You can bring me questions about the project. You can ask me, like, well, what do you expect? I don't quite understand this. What are you expecting? What do you want? We can have all those kinds of discussions. By the way, office hours is another great place to have those discussions. So those of you who want to ask me those kinds of questions, feel free to come to office hours, and I can answer those same questions for you. Okay? So let's jump into hypothesis testing. Let's move that over. Let's see. So you have your chapter on hypothesis testing. You'll do your lessons and your assessments, and you might go, December 7th seems so long away. Well, it gives you time to do this assignment, finish up the other assignments. Some of you have assignments in the past you haven't completed. Remember, you can still do the My Math Lab assignments past the due date for half credit. And a lot of, you might go, half credit? Oh, that sucks. But I'll tell you, on a test average, or a homework average, a 0 hurts you a whole lot more than a 50, right? 50%. And I'll be honest, one of the things I look at when I see I get these emails at the end of the semester that are, sort of people going like, oh, I know I didn't do this, and I waited, but I'd really like you to pass me in this class. It would be great if you could pass me in this class. And so I look at the grade, and it's like, well, okay, so your project was scored pretty low, but, some people just, sometimes not everything you do in life's a home run, right? You think you're ready for the project, you step up it, and it kind of falls flat, and you get a lower score than you would have liked. But then I look at the homework grade, and the homework grade is low too. And it's like, well, you didn't, why would you pass the course? If you got a low grade on the project and you didn't bother to do the homework, then what is the reason that you should pass this course? And usually if you read the email, it's something along the lines of, well, I really, really want to pass. Well, that's not how college works. We don't pass you because you want to pass, right? And that's not how sort of real life works anyways. You don't get things just because you want them. You have to make them happen, right? So in a case where a grade is borderline, where should this person pass this class? Should they not? If I look and the homework grade is low, I go, well, they didn't even participate. They didn't even do the things they were supposed to do. Why should this person pass the class, right? So, right, and that doesn't mean if you do the homework, you will pass the class, but by not doing the homework, there is a very high likelihood that you will not pass. It's very hard to pass this class by not doing the homework. One, mathematically, if you don't do the homework, it lowers your score significantly. But also, like I say, even if you're borderline on one of these grades where it's like, oh, they're so close, should I bump them up to the next one? And I look and you didn't really do homework. It's like, well, why do they deserve to have their grade bumped up? They didn't even do the work that they were supposed to do. Like, clearly they didn't take the class seriously, and then we're just hoping at the end of the semester that telling me you really, really want a B or an A or whatever grade somehow is going to make me give it to you. So just make sure going into the end here, have that homework grade as good as you can. That's a pretty good justification for, I really put effort into this class. It's hard to justify to me that you put effort into the class if your homework grade is low, right? And that doesn't mean I'm going to boost your grade if you did all the homework. But like I say, if it's close, that's my go-to. I look at the homework and go, yeah, this person didn't really care. They didn't really care about the course. They just thought maybe they'd send an email and magically I would fix it for them. So even if you have some past assignments that are low, go get some 50s on those, because that average, zeros just kill your average, right? Imagine you get 100% on one assignment and a 0 on the other. You don't have a 50% average. Well, what if you get 100% on one assignment and a 50 on the other? You don't have a 75% average. That's now passing. So basically do your homework. There's only two things in this course. There's the homework and the project. People think they're going to pass without doing homework. That doesn't happen. So, okay. So with that said, we get into hypothesis testing. And again, do not look at hypothesis testing just as, how do I get StatCrunch to do this for me? That's important that you're able to do that. But that's like the beginning of the journey, right? That's like maybe the first 10% is figuring out how to do it on StatCrunch. The other 90% is understanding what you're doing, being able to make sense of it, apply it to your project, being able to explain it. If you can't explain to someone in your group what your conclusion is with your hypothesis test, that's a pretty good indication you need to do more work on it, right? Yeah, so I'll save that. We'll talk more about it on the other end of things, but like, let's get into the hypothesis testing. So we've talked about confidence intervals. Confidence intervals are very important statistics. You see them in published research a lot. Non-statistics people don't really like confidence intervals a lot of time because they were like, just tell me the answer. They don't understand that, well, we don't ever know the answer. We're estimating it. So a confidence interval, some people argue, is a much better rule or a tool to use than a hypothesis test, right? We teach hypothesis testing, and hypothesis testing is important, but there are some instances where people don't want to see your hypothesis test, right? There are journals out there, scientific journals, that have changed their rules and said, we don't want people submitting hypothesis tests anymore. It's all confidence intervals. Because if you do a hypothesis test incorrectly, you can end up making poor conclusions. So it's either, you want to make an incorrect conclusion because you want to mislead people, or you just don't know what you're doing and you do it on accident. A hypothesis and confidence interval is a little bit more... it's harder to mess up, basically. It's harder to screw it up, and the interpretation is harder to screw up. Where a hypothesis test, I find many people, maybe half people, don't really understand what's going on with the hypothesis test when they finish this course. So in statistics, a hypothesis is a claim or statement about a property of a population. So we'll look at some examples in just a minute, but you have something that you think may be true, and you want to test statistically if it's possible or not. Or like, what is the level of certainty with which you can say this thing is true? So, let's just say that this year we took a measurement of the students at the college, and we found that the proportion of students who support a vaccine mandate, let's just say that it's 0.8. Okay, and then let's say that next year we remeasure it, and the proportion that we get next time is 0.79. Well, if you're sort of inexperienced at statistics, you could go out and say, well, this year it's 0.8 and next year it's 0.79. That means it's dropping. That means the number of people who support the vaccine mandate has dropped. And then you'll see headlines. News is terrible with statistics. You'll see headlines that said, oh, the number of people supporting the vaccine mandate is dropping. And then you read, and it dropped from 0.8 to 0.79, which is, first of all, a very small drop. But you want to stop and think about that and say, can we really make the claim that it dropped? If it was 0.8 and now it's 0.79, how sure are we that indeed the proportion did drop? You might say, well, isn't it clear? It was at 0.8 and now it's at 0.79. But remember, we don't really know for sure it was at 0.8 last year and 0.79 this year. Those are the results we got from sampling. And as we know, sampling is almost never perfectly on the nose, right? It gets us really close to where we need to be. It gets us in the vicinity, but there is sampling error. There is variation from sample to sample, just like I've been giving these examples that if I send all of you out to go ask people on campus about the vaccine mandate, you're not all going to come back with P equals 0.8 for your proportion, right? Some of you are going to get 0.82. Some of you are going to get 0.75. Some of you are going to get 0.77. So, the reason then, if we're just going to look at those point estimates, would be, well, at 10 o'clock when he asked, then support for it was 0.82. And then at 3 o'clock when she asked, it was at 0.74. Like, that would be ridiculous, right? That would sound like, well, in the course of a day, it's changing. No. But it's the same reasoning over the course of a year. Maybe that the feelings are changing, or maybe it's just the random drift that we get from sampling different groups where we get slightly different numbers. So that's one of the claims we want to be able to make and figure out, which is if we measure that the vaccine mandate has 0.8 the proportion of people who support the mandate is 0.8 one year, and the next year we measure 0.79. can we make the claim that it's dropped, or does that fall in the realm of just normal sampling variation? We don't really know, right? Well, a hypothesis test will help us figure out the probability that it's just normal sampling drift, right? That the values drift a little bit when we do different samples, we get slightly different answers, or do we really see a change, right? So this would be easier if, say, this year we measure the proportion of people who support a vaccine mandate is 0.8, and then next year when we measure the support of the vaccine mandate, it's 0.4. So from 80% to 40%, in that case, you can probably go, yeah, I think I know how these statistics are going to come out. I think we're going to be able to prove there was a drop in support. But if it's going from 0.8 to, say, 0.75, you don't know. Is that just sampling, randomized sampling variation? Or is there really, was there a measurable drop that we can go on, the news and say, yes, there is less support now than there was before? And that's subtle, because if you just blindly look at the numbers and miss the context of what's going on, you'll say, well, yeah, it dropped. It was at 0.8, now it's at 0.75. Well, but what is the reasoning for that drop? Is it just that we did a different sample, so we got a slightly different answer? Or is it that there was an actual change in people's feelings? So we can test about population proportions, we can test about population means, and we can even test about standard deviations. But usually we'll probably be doing proportions and means. So a few examples. Newspaper headline makes the claim that most workers get their job through networking. Okay, well, most means more than 50%, right? So sometimes you hear the phrase 50% plus 1. That doesn't mean 50% plus 1%, because you would just say 51%. They mean you get half, 50%, and then one more vote or one more count to sort of put you slightly into the majority. So that's the kind of thing we could use a hypothesis test to test that claim. Medical researchers claim that when people with colds are treated with echinacea, the treatment has no effect. Here's a big one, because there's a lot, there's the medicines in this country are regulated by the government, so that people, because there's a long history of people just making things up and then trying to make money off people who are trying to look out for their health, but they're, you've heard the whole thing, snake oil salesmen and stuff like that, where people are go around selling things that aren't really helpful. We even see that today, and there's controversy with many items that are available in today's society, and we need to know, are these things helpful, right? You can look up a whole list of things that you're supposed to take when you get a cold. People want you to take echinacea. They want you to take zinc. They want you to take this. There's like 5 or 6 things, right, that are recommended outside the medical community. So you have your actual medicines that are regulated by the government, and then you have things that are not considered medicines, supplements, vitamins, that kind of stuff, not regulated in the same way, because they're not prescribed. They're not specifically for a certain illness. They're not medicines per se, right? So then you run into this where there's a lot of people who, if you go online, you can find lots of stuff that will tell you echinacea is great when you have a cold. It will shorten your cold. You'll have less of a cold, all that kind of stuff. And then you find other stuff to say, yeah, it doesn't really help at all. Well, how are you supposed to tell the difference, right? Let's say that you're a medical student and you want to conduct a test, and you're going to get people with colds. You're going to give them echinacea, and you're going to see if it really makes a difference or not. This kind of stuff, you can't just make these kind of decisions because you read a couple things on a website, right? That's sort of what's happening to our country these days. Is if someone reads it on the internet, then somehow they can decide to believe it. You need to be able to distinguish what is actually true and what is not true, and is the earth flat or is it round, or all this kind of silly stuff that was established long ago. But someone reads something on a web page and all of a sudden they're sort of willing to just go down the rabbit hole with it. So person might be, we want to, what if you have 2 groups of people with colds, and you give, you find that the average duration of a cold for the people who did not take echinacea was 5.4 days. and the people who took the echinacea was 5.3 days. Well, again, is that just the random sampling because we have two different groups that we're measuring? So is it just variation, or really are those groups really at the same value and we're just seeing some sampling? Or does the echinacea actually help, right? So those kind of claims can be tested. The kind of claims like the airline industry, they're very concerned with weight, right? Because the more weight on the plane, the more gas they have to use. They use tremendous amounts of gas, so it's very costly. And then the size of people dictates how close they can jam these seats together. I don't know if any of you have seen it. It's sort of a terrifying realization. They're trying to come up with seats now where you're essentially standing. You're kind of leaning backwards, but you stand up because then you take up less room on the ground. They can cram another 15, 20 people on the plane, but then you're standing for 3 hours, just sort of leaning back into these seats. Those are being tested by the airline industry to see if they want to go with that. So airline industries need to know, are people getting bigger, right? Are people getting larger? Do they weigh more than they did 20 years ago? And there definitely seems to be evidence that people are getting larger. By and large, you look at people from the 60s, you look at people in the 2020s, there's a big difference between weights. But if you want to pick any 2 years, like, what about 2020 and 2000? Do people weigh more than they did then? You might pick a sampling and find people weigh a few pounds more on average, but is that really enough proof, or is that, again, just normal sampling variation that you found when you sampled those two groups, right? Just like I keep saying this, but this is a subtle point that so many students miss. Remember when I told each of you to go out and, hypothetically, and do a measurement for people who support the vaccine mandate? You're all going to come back with different answers, right? Slightly different, hopefully in about the same area, but slightly different. That's that sampling variation. You're all measuring from the same population, but you're getting slight variation in your proportion that you measured. So that's what we need to know. Is there one of the things that we'll test? Is this just sampling variation, or is there really a difference between these two groups? Quality control, which I've mentioned numerous times in the class. When new equipment is used to manufacture aircraft altimeters, the new altimeters are better because the variation in the errors is reduced so that the readings are more consistent. So you spend all this money bringing in new machines. You want to know, are they actually doing a better job measuring things? Okay. Here's a big caution, which kind of goes into the stuff I've been saying all semester. And it applies to the whole class, but especially now. When conducting hypothesis tests as described in this chapter and the following chapters, instead of jumping directly to procedures and calculations, be sure to consider the context of the data, the source of the data, and the sampling method used to obtain the sample data. Again, being able to do a hypothesis test in StatCrunch is effectively, it's not good, right? I mean, it's like the minimum thing you need to do. Like when you turn in something for an assignment in a class, what's the minimum you need to do? Like put your name on it so the teacher knows who you are. But that doesn't really mean you've done the assignment, right? It's like necessary but not sufficient. It's necessary for you to put your name. It's not sufficient to get a good grade. It's the same thing here. They're saying look at the bigger picture, because if think about what you're learning in a class and compare that to your usefulness in the real world. How secure are you in your job if the thing you know about statistics is how to punch 3 buttons? Like assuming you're at a job that requires some statistics, which hopefully you probably are if you're required to take this statistics course. I can punch the 3 buttons that I need to in order to get a hypothesis test. And then your boss says, well, yeah, I can hire someone else and teach them those 3 buttons in about a minute. So that doesn't make you very valuable in the workplace, right? What makes you valuable is that you can push those 3 buttons to run your hypothesis test and then use that to make some kind of informative recommendation or conclusion that is actually going to be meaningful to someone. That's a thing that's harder to replace. Button pushing, it's basically already been replaced, right? You won't have a future. There won't be jobs for you by the time you graduate if all you do is like memorize some button pushing. Because in 10 minutes we can program a program to do button pushing, you're now been replaced by software. So you just realize that it's the context and the understanding behind the hypothesis test that is important. You being able to conduct a hypothesis test is not important. You understanding what you figured out is important. Okay. Right. So here, this one's tricky for people. People sort of intrinsically, there's an intrinsic understanding of the logic behind certain parts of the hypothesis test, but I think people get bogged down in language and, memorizing things, and they lose that intuition along the way. So here's our rare event rule for inferential statistics. And this will sound reasonable, but you need to figure out how to connect this idea to the hypothesis test. So let me read this. If under a given assumption, so a given assumption means you've assumed a thing. Say, well, I assume that this is true. I don't know if it's true, but I'm assuming it's true. So then we're just acting on that. Let's assume that what you're saying is true. Then we'll move forward. So if under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. You do this every day when you listen to people, and you determine if you think those people are telling the truth or lying to you. Okay? If someone comes and says, they say something to you that is highly probable, then you go, okay, that's probably the case. But if someone comes to you with a story that is outrageously improbable, you're going to go, I don't believe what that person just said to me. That's ridiculous, right? So first day of class, on-campus classes, people tend to be late a lot, right? And then people come in and they're going, the parking lot was a mess. I couldn't find a parking spot. Sorry, I'm 15 minutes late. Won't happen again. Okay, that's believable. There's a high probability that that's true because hundreds and hundreds of students, maybe thousands of students, have trouble with parking on the first day of class because they forget that if you have an 8 a.m. class on the first day of school, you shouldn't show up and pull into the parking lot at 7:59 or whatever. You're not even 7:55, and they get there and go, oh, there's no parking. Right? So that's believable because it's highly probable because it happens all the time. So when a student tells me that on the first day, I go, okay, whatever, come sit down. Don't just plan better next time. Don't cut stuff out at the last minute. That's fine. Probably just going to give that student the benefit of the doubt. If someone comes on the first day of school and says, I'm late because I left in time, but then on my way to school, a car pulled up and 20 clowns got out and they beat me up and then put me in their car and they took me away to where I was, abducted by aliens, and they took me up in their spaceship and then they flew me around and then returned me. That's why I'm 15 minutes late to class. Is that possible? Yeah, sure. It's possible that some clowns had it in for you and then the aliens came across you. That is a possible thing that could happen in the universe. But is it probable? No. It is improbable on a level where if you tell me that, I'm not going to believe you. Why don't I believe you? Because it is so improbable. Right? So a student telling me, oh, I'm late because the parking lot's crazy right now. I couldn't get a spot. Sorry. That's probable, so I believe them. The other story that I told you, very improbable, I don't believe you. So we just do this as humans, where we say if someone gives us a story and it has a high probability of occurring, yeah, okay, probably true. If it has a very, very small probability of occurring, we don't believe them, right? That is part, not all. That is part of what you need to apply to the hypothesis test. Now, I think where people have trouble translating that over is the assumption part. If under a given assumption, right? So what is the assumption in your hypothesis test? There's basically what we do with the hypothesis test is we set up one assumption. You can't have 5 assumptions because then if you get a really low probability, you go, well, is assumption 1 the one that's wrong, or assumption 2 the one that's wrong, or assumption 3 or 4 or 5? You got to have one assumption. Everything else is facts, right? Indisputable evidence, but one assumption. Then if things are really, really improbable, then there's only one culprit. It's that one assumption. So when you're doing these hypothesis tests and you're doing the homework on hypothesis tests, pay attention to the assumption and get used to thinking about it in a way of, okay, this is my one assumption. Okay, so that's the thing that's either right or wrong. Okay, you don't want to. We're not going to start taking facts and overturning those. Like, we know those things are occurring, right? So pay attention to the assumption along the way that's being made. So, and the assumptions basically come down to the thing you're testing, the things we were talking about up here. So the medicine, your assumption could be there is that when you treat people with colds with echinacea, there is no difference in outcome. That's an assumption. Okay, that's either going to the test is either going to determine that is highly probable or highly improbable. But that's the assumption. The other things we know, right? We know that this is occurring on Earth. We know that it's occurring with humans. We know that some people were given echinacea and some people were not. These are all things we know because we did them. The one thing we don't know is if the echinacea makes a difference when you take it when you have a cold. That's our assumption. That's the thing that we will either show to be and I have to be careful because we don't really show whether things are true or false. We just show whether we sort of can reject the claim or not. So I want to be careful here setting that stage. That's another tricky thing that trips students up. So does that make sense? You have a claim. It's generally the thing you're trying to hopefully give evidence for. We don't really ever actually prove anything, right? In statistics, you can't it's not like one thing and you go, there it is. We 100% have figured this out. It's more like we're pretty sure this is what's occurring and we have strong evidence for it. But you never really prove things in a sense. Like, you'll hear people say things now that people that don't really understand science and stuff, and they'll say, well, that's just a theory. Well, yeah, being a theory doesn't mean that we don't have strong evidence for it. Gravity is just a theory, right? We have a theory of gravity, but no one's out there questioning gravity. I don't think there's gravity. We can make predictions about gravity. I can have a ball and drop it, and I can predict to a high degree of accuracy, millions of a second, how long it's going to take for that ball to hit the ground. That's pretty well established, even though it is the theory of gravity, right? We can use that evidence in strong ways. It's the same thing here. We never in statistics know something 100%, but we can build evidence that we're really, really sure that we know what we're talking about, right? So we want to be careful with that word prove because we can use it incorrectly. Okay, let's get into some ideas here. Where is my definitions? Okay, so working with the stated claim, null and alternative hypothesis. So when you do a hypothesis test, you have two hypotheses. One is called the null hypothesis, and this is usually indicated with H sub 0. The null means nothing in mathematics, so sometimes it's represented with a 0. And then the alternative hypothesis, you'll see, depending on where you're looking, it gets a little bit different notation. So either H1, that's a popular one, or HA. Those are your alternative hypothesis. And they are basically, in general, they are going to be the complement of your null hypothesis. So if my null hypothesis is that the proportion of students who support a tobacco ban is less than 0.8, then the alternative hypothesis would be the opposite, which is what? That the proportion of students who support did I say vaccine mandate for that one? For if my null hypothesis is that the proportion of students who support a vaccine mandate is less than 0.8, then my opposite of that would be that it is greater than or equal to 0.8, right? It's like the opposite end of it. So basically what's going to happen is if we reject our original one, that leads us to say that there is evidence for the alternative. You have to have we're either going to show, well, I even have to be careful about saying that. We'll get into that. Let me explain a little bit more before we get into the details. But the null hypothesis is usually the thing, like, you don't want to make the null hypothesis the thing you're trying to prove. And this definitely confuses students because, like, the null hypothesis is the main thing that you construct in your hypothesis test, but we do it a little bit backwards. We actually want the thing that we want to prove to be the alternative hypothesis. Now, why is this? Why wouldn't I just make it the null hypothesis? And this is like a sticking point where I see people even do this in their projects. By the time we get to there, they haven't sort of put this piece together. The hypothesis test never gives evidence to support the null hypothesis, right? You don't want to say that. You don't want to say, we ran this and it had a high p-value, so this proves the null hypothesis, or this shows that the null hypothesis is true, or something like that. We cannot give support for the null hypothesis. What we're actually hoping to do is reject the null hypothesis, right? By getting a p-value, that's our probability. There's a couple p's that go on with them. So you have to be careful. There's a few p's that go on with hypothesis testing. What we actually hope to do is reject the null hypothesis. Well, if we've rejected the null hypothesis, then what's left? The alternative hypothesis. So if you're hoping to have a certain outcome, and I don't mean by being like devious or trying to be misleading or anything. I just mean if you're a researcher and you're like, let's say you're a researcher and all your patients keep coming to you saying, well, when I get sick, I take lots of echinacea because I read on the internet that helps. And you want to conduct a study that shows that there is no difference for people with colds who take echinacea, then your null hypothesis should be the boring, run-of-the-mill thing, which is that there actually that would be tricky the way we set that up. Because in that case, you'd actually be proving, well, let's see. Let me state it a different way, right? The null hypothesis is generally the thing that's like already expected. It's not or accepted. It's not weird or like it's just kind of a boring statement, right? Your alternative hypothesis is the thing that you want to give evidence for. And it's the opposite of your null hypothesis. It is the complement. It is what's left over when we show that the null hypothesis is true. Because we can come up with really good evidence to reject the null hypothesis. We can never come up with evidence to accept the null hypothesis. Do not say that in your project. Do not say this p-value was high, so we accepted the null hypothesis. That shows that you understand zero about how a hypothesis test works. If you want your hypothesis test to actually make a statement, you need to reject the null hypothesis, okay? Right. Right. So here they kind of say what I was talking about. If you're conducting a study and want to use a hypothesis test to support your claim, the claim must be worded so that it becomes the alternative hypothesis. Okay? You can never support a claim that some parameter is equal to some specified value. We can't do that. So basically, whatever you think is the outcome in your project, that's the alternative hypothesis in your hypothesis test, and then the complement of that becomes the null. So whatever's left over outside of your alternative hypothesis, that becomes the null hypothesis, right? Right. So let's do an example here. Identifying the null and alternative hypothesis. So consider the claim that the mean weight of airline passengers, including carry-on baggage, is at most 195 pounds. The current value used by Federal Aviation Administration. Follow the three-step procedure outlined below. So this would be the case where, right now the Federal Aviation, the FAA, Federal Aviation Administration says, yeah, the average weight of a person taking a plane is 195 pounds. Well, maybe that was figured out 10 years ago, and you're coming in as someone who's in the FAA and you're like, I think we need to update this recommendation, right? I think people have gotten even bigger than they were before. So you're going to see if you can statistically show that people have gotten bigger, okay? So we want to express the given claim in symbolic form. The claim that the mean is at most 195 pounds is expressed in symbolic form mu less than or equal to 195 pounds. And you go, wait a minute, is that a typo? Is that a mistake? No, because remember, the thing we are trying to show, right, and we want to show that the mean weight of passengers is at most 195 pounds. If that's what we want to give evidence to, that has to be the alternative hypothesis, not the oh, did I read this wrong? Consider the claim that the mean weight of airline passengers is at most 195 pounds. Okay. At most 195 pounds. Right. So that matches up. Mu less than or equal to 195 pounds. We haven't talked about the null yet. So the opposite of that, if mu is not less than 195 pounds, then the opposite must be that mu is greater than 195 pounds, right? So just take, if something's not less than or equal to 195 pounds, then it's greater than that. So you have these two statements. Of the two symbolic expressions, mu less than 195 and mu greater than 195, basically the way this book particularly does it is they want you to put the equality with the hypothesis test, right? So here, of the two symbolic expressions, mu less than 195 pounds and mu greater than 195 pounds, we see that mu less than 195 pounds does not contain equality. So that's one of these is a less than or equal to, one of them's just greater. There's no or equal to part. That's what they're talking about when they talk about the equality, right? So we let the alternative hypothesis H1 be that mu is greater than 195 pounds. Yeah, right, because that's the thing we're ultimately seeing if we can show. Also, the null hypothesis must be a statement that means equals 195 pounds, so H sub 0 is mu equals 195 pounds. So what you want to be able to do is read these problems and then turn what they're saying in words into hypothesis tests, right? So something that is, remember, mu is just the mean. So the mean is less than or equal to 195 pounds, or the mean is greater than 195 pounds. You're pulling that from the problem, and then you have to figure out which one is which. Good news is you don't have to do these formulas right here. You're not going to have to calculate those. Those are going to be done inside of StatCrunch, right? So don't worry about that. And it'll show you, you'll see, remember there's those buttons about show me how to do this in StatCrunch, and then it shows you exactly what buttons to push, and you can go through and do that. So we don't even have to worry about critical values. Oops. But you will be aware you still do have to create a cutoff. So remember when we did a confidence interval, we had to decide, do we want a 90% confidence interval? Do I want a 95% confidence interval? Do I want a 99% confidence interval? And you can choose other values too, but those are kind of the three most popular ones. We need a value for our cutoff for the hypothesis test, because what's going to come back when you do this is it gives you a p-value. That p-value is the probability, sort of, you can think of it loosely. We'll go into it more in depth next time. Well, here we have it right here. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. So remember back to the beginning where we say, given a certain assumption, what is the probability of this thing occurring? If the probability is very low, then we're in the situation with the, where the clown stole the person and then the alien abduction. The probability of that is very low, so you don't believe it. So we would reject that. Okay? If the probability is very high, where the person's like, well, the parking was bad in the parking lot, and the p-value was high, like say 0.4, and we go, that's pretty high probability, we'll assume the person's telling the truth, right? Notice in that case where the person said, yeah, I had trouble in the parking lot, and we found that there was a 40% or a 0.4 probability of that being true. That doesn't prove that the person's right. That doesn't prove that that student really did have trouble in the parking lot. What it shows is that it's a highly probable statement, meaning it's believable. I don't necessarily believe that person, but I also don't have evidence to go, yeah, you're making that up, right? So that's sort of the first instance we're seeing of this situation where the hypothesis test cannot be used to show that someone like that null hypothesis is true. We can only use it to give strong evidence that the null hypothesis is probably false. So don't use this to, like, if you're using a hypothesis test to back up your null hypothesis, you're doing something that is logically incoherent. Logically, it doesn't make any sense to do that. Okay, it doesn't work. So they kind of tell you here, if P is low, the null must go. If P is high, the null will fly. It's kind of silly, but people remember things that are that rhyme. Basically, they also believe things that rhyme. But if your probability is very, very low of something occurring, you're not going to believe it, right? If the probability is reasonable, 0.2, 1 out of every 5 times, you go, okay, that sounds reasonable. That's the idea of this p-value. So you're going to get a p-value out. Now, the question is, well, how do I judge a p-value? Like, what level is low enough that I'm not going to believe it anymore? What is the point at which I go, that's kind of high, but not too high. I don't know if I should believe this or not. That's why it's very important when you conduct a hypothesis test. You figure that cutout ahead of time. The cutoff, where you say, if the p-value is below this critical value, I'm going to reject the null. If it's above this, I'm not. Because otherwise, like, let's imagine you're doing research and you really think it's true. You're like, I really think it's true that this medicine helps people get better. But then what if then you get your p-value out and it's kind of in the range where you're like, well, that's higher than I'm comfortable with, but I really think that this is true. See how that's going to bias your outcome? Like, all those thoughts now, you have all these competing things that are keeping you from making an objective result of your statistics. So that's why ahead of time, before you conduct the test, you have to decide, what is my cutoff for where I'm going to reject that p-value or where I'm not? You can't do it afterwards or you've biased the whole thing. Just like we normally use a 95% confidence interval, we basically use that same level for hypothesis tests as a default, which is our cutoff value is 0.05, right? 0.05 is 5%. 5% is what's left over from 95%. So we're still kind of taking that, in general, we use the default of that same cutoff, but it just looks a little different the way we're using it in here. Okay, so let's stop there. We'll pick up next time with this. We'll talk a little bit more about p-values, and we'll get a little more in depth with the hypothesis testing. So if you're still confused about hypothesis testing, you should be, right? If you think you've understood everything I've said, you probably actually aren't understanding how things fit together. Haven't explained the whole thing of a hypothesis test. We haven't done a hypothesis test yet, right? We have lots of discussion left to have on hypothesis testing, but that's the beginning of our discussion about hypothesis tests. So with that, it looks like I'm out of time. So we will continue this discussion on Tuesday. I have office hours, so anyone who wants to hop into Zoom and speak with me right now, please do. Otherwise, I'll see you in a couple days. All right, thanks, everybody.